Hi, this presentation is going to go over the topic of correlation. And correlations are important in social science because they are the way that we begin to test ideas related to causality. So we collect data, we examine the relationships between variables, and the correlation will tell us whether or not there's an association. You may have heard the phrase correlation does not equal causation, and that's true. But correlation is one of the key criterion. The other two are time order and non-spuriousness. And for those, we need to have longitudinal data and techniques such as partial correlations or regressions, uh, both of which we'll examine at other times. So correlations, they, when graphed, look something like this. We have an x independent variable that is specified to predict some kind of y dependent variable. And we see different possible outcomes here. This would be what we call a negative linear correlation, where as x increases, y decreases. Also called an inverse correlation. Or here we've got a positive linear correlation, where as x increases, y increases. Here we've got just a scattering of dots, so there's no relationship, although maybe it looks like there's kind of one there a little bit. And here we've got something called a nonlinear correlation. We're not going to get into that in this particular presentation, but perhaps we'll come back in another time. When we're interpreting the correlation, the value ranges all the way from -1 to 0, and then all the way up to 1. One of the things we try to evaluate is the strength of the correlation, and the closer we are to either -1 or 1, the stronger the relationship will be. Now, if it's close to -1, that just means it's a strong negative or inverse correlation. And if it's close to 1, then it's a strong positive correlation. All right, so those terms, positive and negative, refer to direction. More specifically, if an increase in one variable leads to an increase in the other, they're positively related. Another way of saying that is, as one variable decreases, if the other variable decreases, they are also positively related. The inverse, which I like better than the term negative, because I think it can infer like negative values, and again, if two things are going in the same direction, they're positively related. Inverse means as one goes up, the other goes down, or as one goes down, the other goes up. All right, so those are the ways we interpret the correlation. And this is the formula for calculating the correlation. And of course, these formulas can be scary at first glance, but as we walk through an example, we'll see how this equation looks in action, and it's not nearly as scary as it starts off looking. So what we've got, the Pearson's R is equal to the sum of the product of the x and y variables minus the sample times the median of the x and y variables. All of that is in the numerator. In the denominator, we've got the square root of another product. Within each of these products, we've got the sum of x squared minus the sample size times the average squared, right, for both the x and the y variables. All right, so let's come look at an example. High school guidance counselor is interested in the relationship between proximity to school and participation in extracurricular activities. Collects the data on distance from home to school in miles and number of clubs joined for a sample of 10 juniors. So we've got the miles in this column and the number of clubs joined in that column, and these are the individual students. So if we want to come up with a Pearson correlation, we need to lay this all out, and it helps to do so by putting this table together. These are the same x and y values from the previous table. Here we've got the square of those values, and over here we've got the product of those values. And down here we've got the sum of the x's, the y's, the x square, the y square, and the xy product. Okay, and we'll need all of those to work through this equation. And so you can see those values are being plugged in here, 299 right there. 10 is the sample size, and that appears in those places. The average, since we have 10 and this sum is 57, is going to be 5.7 for x. You see that here and there. And the average for y, because there are 10 and the sum is 41, is going to be 4.1. So there's the average y right there and there. And once we just kind of plug those values in and we run through the calculations, we get to a correlation of 0.84. Now 0.84 is a pretty strong correlation because it's close to 1. And it's a positive correlation, so as increases in distance go up, so too do the number of clubs. So the next thing we have to do is look at whether or not this is a statistically significant correlation, and for that we need the correlation table. You'll be able to find that in our Blackboard shell if you're taking the class. If not, just Google correlation distribution table for statistical significance and you'll find some of those tables online. The cutoff for 10 degrees minus 2, because our sample is 10, so degrees of freedom is n minus 2, so that gives us 8 degrees of freedom. And at the 0.05 level, alpha, we find a value of 0.6319 is the cutoff, and 6.84 is greater than that. It is a statistically significant relationship. So another thing we can do is calculate a t-statistic for Pearson correlation. We need this formula to do that, where it's simply t equal to the Pearson r over the variance of r, the standard deviation of r. And the standard deviation of r, if we unpack that, is the square root of 1 minus r squared over n minus 2. So again, not too complicated here. This will be the value we need for our t-statistic, which we can then compare to a critical value from the t-distribution, again available on the Blackboard site, or you can just Google the t-distribution, with degrees of freedom of n minus 2. Okay, so now Pearson correlation of minus 0.85 was found for a relationship between age and racial tolerance for a sample of 10 students. And so our degrees of freedom is going to be 10 minus 2, or 8. Here's the equation we just looked at. If we plug in the values of minus 0.85 for the correlation and 10 for the number of respondents, that will come down to a value of negative 4.5. And if we look up our t-distribution at the alpha 05 level, we find a cutoff of minus 2.306. And since minus 0.45, 4.5 rather, is bigger than that, this is statistically significant t-test. All right, so that's how we got to the t-test, the t-score rather, sorry. Okay, so the next thing we need to look at is something called the partial correlation. Now this is important because sometimes we want to know the effect of a relationship while controlling for a third variable. And that's important for one of the second criterion of establishing causality, which was non-spuriousness, which we mentioned earlier. Controlling for variables ensures that a correlation is not spurious, or at least it helps provide evidence for that. So the partial correlation, here's the formula. You've got the R, Pearson R, and the notation here of x, y of the two variables, comma z, means we're controlling for z. Okay, so we've got the correlation of xy minus the correlation of xz times the correlation of yz. And all of that is over the square root of 1 minus the correlation of xz squared and multiplied by the square root of 1 minus the correlation of yz squared. Okay, so we'll look at some values that we can plug in there. We should first point out we can also find a t-score for that. And actually, we will work through an example in a handout that I'll give you that will allow us to look at both. All right, so the t-score of xy is going to be the correlation of xy times the square root of n minus 2 and over the square root of 1 minus the correlation of xy squared. Okay. Now, just to kind of finalize our discussion of causation, sometimes we see a correlation that is not causation, so we have to ask a few questions. Are we sure that it's actually x that causes y? So in other words, do we really think there's a direct cause and effect relationship? And hopefully we'll use theory to help us think about that question. Another question is there a possible reverse cause and effect? Or in other words, is it y that's causing x? And for that ordering of variables, we really need longitudinal data to establish. And you actually need 3 points in time. We haven't gotten into the longitudinal analysis. That's a lot more complicated. Another question, is it possible the relationship between the variables can be caused by a third variable? Right, so doing the partial correlations allows us to address that question. Or if it's a combination of several other variables, for that we'll need to switch to multiple regression, which we'll take up in the next presentation. Finally, is it possible the relationship between the two variables may simply be a coincidence? And that's really about the spuriousness question of causality. And hopefully if we have the right variables in our models, our regression models, or our partial correlations, we should be able to sort that out. Alright, that's going to do it. Thanks for watching.